Hello, good afternoon, everybody. Dave McGuire with MERA. It's my pleasure to welcome you to today's webinar. We are going to be talking about cleaning sensitive electronics for remanufacturing today. Pleasure to be joined here today by Hubbard-Hall Incorporated, who's the presenter of today's webinar. We work very closely with Hubbard-Hall for cleaning applications in the remanufacturing industry. Today's webinar will be presented by Mike Valenti, Product Manager, Cleaners and Non-Ferrous Surface Preparation with Hubbard-Hall. Mike's contact information is there should you need to contact him throughout today's webinar, or if you have any follow-up questions for him, he'll be happy to help you out. Regarding Hubbard-Hall, you can always visit them at hubbardhall.com. They've got a great website of different chemistry applications and solutions available for you on the market. And obviously today we're going to be talking about some of those unique options that they have for cleaning those sensitive electronics that more and more remanufacturers are getting involved with as we see the automobile and commercial vehicle market move into advanced technologies. A couple just housekeeping procedures before I turn the floor over to Mike here today. I did want to mention our upcoming MERA Sustainable Manufacturing Conference, Fall 2019. The conference date, time, and location is there up on your screen at this period of time. It's September 30th through October 1st. It's going to be in Detroit. On day one, we'll be at the Automotive Hall of Fame. And then day two will be at a local hotel where we'll be in the Detroit Dearborn region. We're going to be doing some tours of Detroit during that period of time, Detroit Diesel, that is, in their facility. And we've got a number of great things scheduled. You can go to our conference website at sustainablemanufacturing.com for more information, to see the agenda, the special events we have on hand, the venue, hotel, and of course to get your tickets. So if you haven't joined us yet and you're still looking to make preparations, I encourage you to attend. We've got quite a bit of people coming to this year's conference, could be our best ever. So if you're not signed up, we'd love to get you helped out there. A couple other procedures here. We've got a number of other upcoming webinars. We're going to have more on the docket than what you're seeing on your screen here today, but just to help get you started for MERA members, we have an upcoming advocacy call to get you in tune with what we're doing in terms of federal and state advocacy updates. It's on September 18th at 2 p.m. Eastern. And September 24th, we're going to be doing kind of a state of the association, an update on what MERA activities we've been involved in, also ways to get involved throughout the remainder of the year, and what we're seeing in the marketplace and how members can engage through the association. October 16th, we just launched a brand new webinar in conjunction with Amazon. A number of our remanufacturers are exploring options, if they haven't been already, to selling their products through online channels. This is going to be talking about specifically protecting your brand and your intellectual property on an online channel like Amazon, going through their brand registry. So if you have particular brand items, the product lines, maybe you're an authorized remanufacturer for another OEM manufacturer, and you'd like to start selling through those channels with authorization, they're going to be talking about all those different unique processes of how you can do that and how you can work within their system to make sure that your intellectual property is protected. Because the last thing that we want to see is have our remanufacturers move online and then we don't have the proper protections in place to protect your brands. For today's webinar, should you have any questions, and we highly encourage you to ask them, you can use your GoToWebinar software with either the questions pane or the chat pane. These are in the software, usually on the right-hand side of your screen unless you've moved it. So go ahead and use those options. The other thing that's available to you is there's a raise your hand option on the attendee dashboard. If you use that, we can use that to reach out to you via chat to gain your question as well. If all else fails and you still want to get your question in and you're struggling with anything software-wise, go ahead and shoot us a note at info@mera.org. We'll be monitoring that and be able to ask your questions that way. So with that, that's all I have for the time being, and it's my pleasure to introduce Mike Valenti with Hubbard-Hall, who will take the rest of the time here for the agenda. And I'm turning control over to you right now, Mike. There you go.
Okay. Everybody should see my screen now. Good afternoon. I'm Mike Valenti with Hubbard-Hall. David mentioned I am the product manager for our cleaning business. My primary areas of responsibility are for our aqueous cleaners also for our solvent cleaning products. And I also have a strong focus on the non-ferrous metal applications area. So today I'm going to talk a little bit about cleaning electronics with a bias toward the automotive industry and how the automotive industry and cars in general are going to be changing and how we're going to handle cleaning and remanufacturing some of those parts. So let's talk a little bit about electronics and a little bit of history.
Mike, really quick, we're getting some, we're seeing your GoToWebinar software screen. If you can just click that, the option to minimize it.
Okay.
It's the orange button. That might help us out.
Yeah, I'm sorry.
Maybe drag that to the side of the screen as well.
Yeah, okay. There we go. Sorry.
Perfect. Thank you.
Good. Yep. So let's talk a little bit about the history of automobiles and electronics. So let's look back into the late 1950s. The Chevy Bel Air. All we had on cars in the 50s and 60s and even in the 70s were very few electronic components: the horn, the lights, the radios, windshield wiper motors. So very few things that we had to worry about as far as cleaning or remanufacturing an automobile in the 50s and 60s. So let's look at cars today. I've given this talk before, and I always say that automobiles today are like computers with four wheels. Everything on a car is controlled by a computer and has electronics. I know I bought a car a couple of years ago, and they offered me a package for just for the electronics, an extended warranty package. Because of the cost to replace some of these components once your warranty runs out has become very expensive. So let's look at the vehicles of tomorrow. Everybody talks about level 5 and fully autonomous vehicles, cars that are going to be driving themselves. There's going to be a lot of things that are important. If we read the news today and we read about Teslas that are being self-driven, being in accidents, the technology hasn't evolved quite yet, but eventually it will be. So failure won't be an option. All these systems on cars are going to be required to be fail-safe. So cleanliness is the number one component for several remanufacturing industries, and we call this critical cleaning. And if you look at the areas where this is most critical, of course, is aerospace, the high-end electronics industry, and also in military applications. But now we're going to start talking about critical cleaning and extending that into the automotive industry. We're going to be seeing lighter and stronger substrates. As everybody's aware, more and more cars are moving to aluminum and away from steel, more exotic alloys. All types of plastics that are going to be required on these electronics. Other types of non-metallic surfaces. So when we talk about cleaning now in the automotive industry, we're going to be talking about, and I'm going to come back to some of these things. We're going to have a new type of vocabulary for cleaning. We're going to be talking about surface tensions of solvents and water-based systems. We're going to be talking about wetting agents, solubility parameters, vapor densities and vapor pressure. But more importantly, and I'm going to come back to this later in the presentation, we're going to be talking about something called KB value, and I'll explain a little bit more about that as we get more into the actual chemistry of some of the things we're going to need to clean these parts. So when we talk about electronics reman, the first question we're going to ask, is it worth the effort? What are we going to have to consider in remanning an electronic component on a car versus just replacing that? What's the value of those particular parts compared to the percent of the total vehicle cost? Again, what's the cost to replace versus remanufacture? How hard is it going to be to clean the surface? Is it going to be difficult to clean or easy to clean? What kind of contaminants are we going to have to be removing? And then cleaning options. Are water-based cleaning systems, which are standard in the reman industry for automotive, are we going to be able to use water? Is that the answer? What type of equipment are we going to need? And then finally, how sustainable are we going to be able to be in cleaning these parts? So let's just look a little at a chart and a little bit about electronics in vehicles. And what we're just looking at here is, what is the total vehicle cost? And then the total cost of electronics, and what percent of the vehicle is those electronics. And you can see this is going to continue to ramp up. The electronic components in vehicles is going to become a higher and higher percentage of the cost. So the higher it becomes, the more we're going to want to be able to remanufacture and reuse these components. And you can just see kind of the evolution of things as we move forward. So when we talk about remanufacturing in the automotive industry, I'm sure a lot of you are familiar with this. As parts come in, they go through a life cycle. You know, let's say a core of an engine comes in. You know, we look, can we restore this part, or do we need to replace this part? We look at the useful life. There's a disassembly process, a cleaning process, inspection. But we're going to focus on the cleaning process today. So when we talk about the cleaning life cycle for remanufacturing, there's a lot of questions we have to ask. We have to match the process of the substrate. What are the materials made of? What is the optimal process for us to clean? So we're going to have some choices again. We're going to have aqueous. We're going to have solvent. There's semi-aqueous systems. And then what happens to these parts after they're cleaned? Are there processes afterwards that we need to consider? Next thing we're going to have to do is we're going to have to identify the level of cleaning required. So if we look at something like a Class 1 disposable electronic, obviously this is not something we're going to need to worry about reusing or recleaning. This is going to be tossed. This is just a very simplistic example of something that, you know, we would never remanufacture. So even the Class 2, things like cell phones, these may get recycled, but we're not going to be replacing the parts inside of these phones. These phones just get recycled, and at the end of their life, they're replaced. But when we talk about automotive, Class 3, we're talking about critical cleaning. So a great example is to think about LiDAR. LiDAR is a laser ranging system that will be used on these autonomous vehicles. So these systems, any cost of a mistake is going to be unacceptable. So these parts will have to be cleaned. We'll have to consider critical cleaning as the process we use to clean these parts. So in reman, it's all about the core. So in the traditional core restoration processes, we typically think of large, heavy parts, typically steel or steel alloy type parts. You know, your big water pump housings. You know, we get a dirty, rusty part. We're going to clean that and get it back to a state where it can be reused. Pumps and ejectors. You know, we're going to remove the paint. We're going to clean it up, and we're going to reuse it. And again, and reassemble these engines. When we talk about electronics, the core is going to be much different. We're going to be talking about smaller, lighter parts. They're going to have much different alloys, very sensitive components. We're going to have optics, and we're going to have a lot of delicate plastics and things we're going to have to consider cleaning. Even the drive systems here are going to be all electronic. So much different core than we're used to thinking of in the automotive reman industry. So I want to spend some time talking about cleaning just in general, because this is pretty important as we decide how we're going to clean these parts. And the key takeaway here is that cleaning is a process, and it's not just about the chemistry. We're going to talk about the chemistry a little bit later, but everywhere I go, I try to emphasize that cleaning in itself is a process. There are many things to consider. It's not just about picking a certain chemistry and just going with it. So what are all those considerations we have to think about? So there's a set of decision factors that I always go through whenever I evaluate a cleaning process or need. So the first one is, what is the cleanliness requirement? We've talked a little bit about this already. Are we talking about cleaning highly critical parts? Or are we talking about cleaning very rough parts? Is the application aerospace? Is it automotive? You know, how critical do we need to be? The second thing is the part geometry, and I'll show you some examples of this later. This is extremely important when we decide what cleaning process we're going to use. In my facility, what footprint do I have available to put a cleaning process in? Do I have a large area that I can put lots of tanks, or am I limited in space in what I can put in my facility? What are my throughput requirements? Am I cleaning a lot of high volume parts, or am I cleaning a small number of specialized parts? What are the energy demands? You know, do I need to install new power systems? Do I need to upgrade my natural gas into my facility because I need a lot more energy to run aqueous cleaning systems? So energy demands are another big concern. And then EH&S and regulatory. You know, what are the things that I can have in my facility? What permits do I have? What permits do I need? You know, what are the things acceptable to my environmental management? And then, you know, what can I discharge, and what chemicals can I deal with? Waste handling. Anytime you put in a new process or expand an existing process, there's going to be waste. So do I have a wastewater treatment system? Can I handle a aqueous waste stream? Can I not? And then what type of alloys and soils am I dealing with? Am I cleaning iron? Am I cleaning copper alloys? Am I cleaning really sensitive aluminum? And then finally, what's the total cost of the system? You know, what is the total cost I need in order to clean and be cost effective in doing it? So the point here is to think holistically. Don't just think about the chemistry, think about all these things when you're choosing a cleaning process. So we talk about identifying the part. So there's a lot of important considerations when we look at the parts we're cleaning. What is the configuration of the part, the size, the weight? But I want to focus specifically on what we call blind holes. A lot of what we're going to be talking about cleaning in the electronics for automotives, we're going to have a lot of parts that have lots of recessed and areas where chemicals can get that are hard to get to, and even if we can get the chemistry to them, it can be hard to remove it. So this is a key thing to identify. And then identifying the actual contamination. What are the soils? Well, there's really three general types of soils. There's your organic soils. These are lubes and greases. Organic coatings of some type, cart coatings, conformal coatings. The inorganic soils, heat scale, white residues. You see white residues on things like aluminum, rust and corrosion, oxidized solder paste and flux. These are all inorganic soils that will have to be dealt with. And then finally, and what's key is particulate soils, non-ionic, powder coating, just dust and regular everyday particulates that are going to get on these parts on vehicles as they're being driven. And then the substrates, you know, carbon steel, stainless steel, various aluminum alloys, copper alloys, other white metals, the non-metallic, the plastics, fiberglass and epoxies, and other hard surfaces, all things that we have to consider when selecting the right cleaning process. So what are kind of the general cleaning chemistries that we are aware of and we use today? Well, there's really two main chemistries for cleaning. What I call standard degreasing are some pretty simple normal processes. Your mineral spirits, people that just dip parts in a safety clean system, or they use some type of water miscible solvent. The semi-aqueous, the waters, the terpenes, the glycols, the glycol ethers, and then of course the standard aqueous systems where you have water, some type of biller package, and surfactants. Then you have vapor degreasing. Of course, vapor degreasing is a very old process. You have your hydrofluorocarbons, your chlorinated solvents, and your brominated solvents, and then the hydrofluoroethers. And we'll talk a little bit more about these. So I'm going to come back to this chart again, but when we look at a summary of our cleaning choices, we have water, and we look at some of the characteristics of water. What are the good things about water-based cleaning? Well, it's cheap because water's everywhere, right? It's generally pretty safe. Depends on the chemistry, but it's pretty safe. They're pretty safe processes. However, for every gallon of water we use, that water is going to go somewhere. So wastewater treatment is going to be required. Either it's done in-house, or you're going to be having somebody come collect that spent cleaner solution and dirty rinse water, and somebody's got to treat it. Water also requires heat and a good bit of drying. Water systems are going to take up a large footprint. They're heavy energy consumers, but we can find chemistries that'll clean all soil types. Okay. I'm going to argue that water is probably not going to be the best choice for these type of applications. So we're going to talk a little bit more about the solvent options, and I'll come back to this chart in just a minute. So let's talk about solvent cleaning and why we think this is going to be the standard. Vapor degreasing is a very old process. It's been around for a long time. The difference is, and it has a very bad rap because vapor degreasing in the old days had a lot of emissions. These systems gave off a lot of solvent vapors, and they were considered bad for health and environmental reasons. These newer systems, though, are much more advanced and can be made almost readily with no discharge. For those that aren't familiar, it's a very simple process. We are going to boil the solvents. The parts are going to go into the vapor phase. The vapor will dissolve the contaminants from the surface. We will then recycle. Parts will then go into a solvent rinse, and then we will condense the vapor from the boiling solvent and recycle it back into the system. At some point, this boil sump will be contaminated with the particular soils, and we will have to replace it. But this is a very simple process, and like I was saying, the newer systems we actually consider these systems green now because there's no discharge from these systems at all, and we can contain the solvent very readily to keep it from escaping. So again, why would we choose this? Well, there's a lot of advantages to solvents. Number one, it has extremely high cleaning efficiency. A lot of the solvents that are used now are non-flammable. Parts dry quickly. Because we're not using water in these systems, we don't have to dry the parts with heat. The solvents are evaporating, so we get really quick drying. The equipment footprint is rather small compared to an aqueous system. There's a lower overall operating cost. The systems are self-cleaning. Okay, so what are the disadvantages? Some of the disadvantages are regulations. A lot of the solvents today are either heavily regulated or they're looking to regulate them. I will say, though, and we'll talk about the other options that are available today for some of the regulated and solvents, and some of the solvents we believe will be regulated in the future. There is a first fill cost to fill up your solvent degreaser. Once you get past that first fill cost, compared to an aqueous system, you are not going to be replacing chemistry nearly as often. So let's look at some of the different choices for these solvent systems. There's basically three categories you can look at: the hydrocarbon solvents, the fluorinated, and the chlorinated solvents. Hydrocarbon and chlorinated solvents, inexpensive. The fluorinated solvents are the newer technology. They are roughly 3x more times more expensive on fill cost. They all clean well. We can choose solvents in all these categories that can do mild to aggressive cleaning. They're all fast drying. As far as equipment, the hydrocarbon solvents, you need specialty greasers. The fluorinated solvents are drop-in for most machines. I'll talk a little bit about that again in a minute. And chlorinated solvents work in most degreasers with some modifications. The biggest difference here is the hydrocarbon solvents are flammable. The other two categories were non-flammable. Hydrocarbons are VOCs, the fluorinateds are non-haz, and the chlorinateds are regulated. All these systems are low energy consumers. One disadvantage of vapor degreasing is that we can only remove the organic soils with these types of systems. So if we've got to take off heat scale, weld scale, or any other types of rust or anything like that, we will have to use an aqueous step to remove those kind of things. But in electronics, we're not going to be dealing with that as much. So I told you earlier we talked about kV values, and what a kV value is for solvents is it tells its ability to clean. So basically, the higher this number is, the more things and the more ability it has to clean. And one of the good things about solvent degreasing is we have a wide range of kV values. Where we have to concern ourselves with things like plastics, if we use solvents that have too high of a kV value, we could start attacking the plastics and other non-metal components. But because we have such a wide range of solvents to choose from, it gives us a lot of flexibility. So I talked a little bit about part geometry and blind holes. And this is where vapor degreasing really wins over aqueous cleaning for the electronics industry, where you have very small, tight spaces. First of all, it's very difficult to get water into these spaces to clean. It's even more difficult to get the water out. So even if you can get parts like these cleaned with an aqueous system, you're going to have to spend a lot of time and energy trying to dry these parts. With a vapor system, the solvent evaporates, the parts come out clean and dry, and that's not a concern. The other area is flux removal. So where we have electronic components that have fluxes and these very small areas on like an integrated circuit, it's obvious we can't use water here either. So with vapor degreasing, we can actually use low surface tension solvents. We can deflux. We can remove those contaminants without damaging the actual circuit itself. And then particulate removal. When we talk about optical systems and the need to make sure that we remove all the particulate soils off of optics, again, this is a very good method for removing particulates with high throughput without damaging the optics and leaving really clean residue-free parts. A few other things. When we look at aqueous versus vapor degreasing, let's just compare two very generic processes. In the aqueous process, we'll have some type of aqueous cleaner. If we're doing critical cleaning, we're generally rinsing with at least one or more tanks of deionized water. We're going to have ultrasonics. You could see with this many rinses, we could have as many as up to 8 tanks. Cycle time of, 13 minutes, 15 minutes, can be 20 minutes. Just depends on how dirty the parts are. We look at the standard vapor process with ultrasonics. We're doing it about a third of the time. And the biggest difference here is is we're not having to remove the water from the parts after the aqueous system. So that's where the biggest savings is in time. Then let's look at an equipment profile. An aqueous system is going to take up a lot of floor space. You need tanks. You might have cabinet washers, but you'd have to do a lot of rinsing. With a vapor system, much smaller footprint. A lot of companies I go into now are for lean type projects. They're actually putting vapor degreasers in the same area as like the process to process the parts. Instead of trying to process the parts and have to take them like across the plant floor to where their big aqueous system might be set up. They're setting up these things in cells. So it's much leaner process. It reduces the time dramatically. So vapor degreasing allows you to do that. An aqueous system won't necessarily allow you to do that. It takes up too much floor space. And then sustainability. This is a big thing. So we look at the cost of energy in a solvent system versus an aqueous system. We can go through all wastewater treatment. You don't need that with a solvent system. The heating water is an extremely expensive process, whether you do it through electrical heating or you do it through gas. It's an expensive process. Much lower energy cost to run a solvent degreasing system than it is to run an aqueous system. So just to summarize, automotive parts are going to become more complex. So we're going to have to look at better ways to clean when we talk about remanufacturing automotive parts. Choosing the best cleaning process isn't about chemistry. It's a total process. So you have to look at everything involved to decide what process is going to be best for you. We feel that solvent cleaning will be the best option in these new automotive systems for the electronics and the high-end parts area. And then solvent cleaning can be green when all aspects are considered, when you consider the fact that it is a significantly less waste generator than other processes. So that's what I have. So anybody wants to submit questions, so we're ready to take some questions.
Well, thank you, Mike. Appreciate your time here today. As he mentioned, we are open to questions at this period of time. If anybody on the call has questions they would like to ask, you can use the questions pane or the chat pane in your GoToWebinar software. While people are perhaps entering some questions in there, I do have a couple that came in during your presentation there, Mike.
Sure.
The first one is, and I think you might have touched on this briefly, but maybe if you can expand on it a little bit. Can I use newer solvents with my current equipment?
So the newer solvents will need, if you look at the standard vapor degreasers, there's really two types. There are the single condenser units, and the newer ones are double condensers. If you have an old vapor degreaser that only has the one set of condensers, and you're looking to use some of the new inert fluorinated solvents, you will have to invest in a new degreaser with the double condenser system. And the reason this is some of those solvents are blends, and some of the components when the parts are up in the vapor stage, as they move across into the rinse stage, will evaporate out if you don't have that secondary condenser system. So it just depends on the type of degreaser you have. But the newest, latest solvents will need a double condenser system.
Great, thanks, Mike. Another question here, and this is perhaps moving more into the application side. So you may or may not be able to answer this one, but I'll go ahead and ask it. What are the typical components that are possible to keep or that you have to remove during the remanufacturing process?
What are the typical components?
Correct. That either can be kept or that have to be removed.
Oh, you mean actual components? Yeah, it's hard for me to answer that. Because I think part of the reason is there's not enough history yet to decide. But anything that's exposed, generally is going to be exposed to the environment, to heavy duty soils when cars are driving. I think engine components and things like that are sealed, those are going to be much easier to replace and clean than, say, the electric differential of a gearbox on an electric vehicle. But yeah, I don't have a exact answer, because I think part of the issue is we don't have enough history yet to know what's going to be easy to recycle and what's not.
Right. Another follow-up question here, maybe perhaps on the same item, then actually another one coming in here as well. Specifically regarding plastic components, maybe like housings in this instance around sensitive electronics. The degreasing process, is that able to cover both aspects of the application for cleaning?
You're talking about, can we clean the plastics as well? Yeah.
At the same time as the electronics. Yep.
Yeah. So it's a matter of, I talked about those KB values. It's a matter of choosing the right solvent system that will not damage the plastic components. So the answer is yes.
Okay, great. Other questions coming in here. How do you control that the cleaning operation is really effective? Somewhat of an open-ended question there.
So how do we know it's been effective, or how do we know the parts are
correct.
clean?
Basically, how are you basically confirming that cleaning operation has been effective?
So there are a number of different methods to determine if parts are clean. There are highly scientific ways to determine parts are clean. I've seen some very sophisticated measurement equipment that measures the surface reflectivity via electron distribution. I have seen people use something simple as a Dines test, where you are applying a known surface tension liquid to the surface, and you're looking to see what the free surface energy of the surface of the part is. And typically with that, you have to have what a known clean part is, and then you can correlate that to that measurement. There are other markers you can introduce. A lot of people do fluorescence testing. I do that here sometimes, where we shine a fluorescent lamp and we're looking for residual lubes, oils, greases, and things that will fluoresce in the ultraviolet. If there's stress cracks in the metal, this is particularly seen in aluminum, you can actually see the fluorescence. So if you see the fluorescence, that means those particular soils have not been removed. And in some cases, I know in the automotive industry, for the some of the undercarriage parts of cars, the steering mechanisms, they actually purposely run the parts through a bath of a fluorescent dye. Then once the parts are clean, they run them through a black light booth. And if they see any fluorescent tags, they know they've got areas that haven't been cleaned properly. Some of the lubes even have fluorescent markers in them, so that you can see if they've been removed or not. So those are some of the typical things you can do.
Great, thanks, Mike. And maybe that can be a follow-up webinar with one of our partners in the future in terms of testing requirements for these sensitive electronics.
Yeah, there's go ahead.
Oh, no, please.
No, I was going to say, there's actually some cleanliness clinics you can go to where they talk specifically about all these things. There's a professor at Sam Houston State University who I have a relationship. His name is Dr. Darren Williams. And Dr. Williams has an entire research group dedicated to testing the cleanliness of surfaces. And in fact, next year, we're doing a cleanliness seminar at Sam Houston State, and that'll be so I'll plug him a little bit, but that's one of the things that he'll be doing at the seminars, talking about how to measure cleanliness. But he has a whole research group that does that. You can Google him very easily.
And Mike, your contact information is available, so if anybody has any need to get in contact,
sure, anybody
with
can. Yeah, they can call me or email me.
Good. General question here is kind of a longer question came in here, so I'll ask one of the shorter ones. A number of folks asking if the presentation from today will be available. Will that be made available to attendees
Sure.
following the call?
Absolutely. Yeah. I'll send it to you. I'll send it to you. Is that how we? Or
yep.
people can just
I'll
request
go ahead
it
and take it,
if
Mike,
they
and
want
we'll
to
distribute it to the attendees. Perfect.
Yeah, that's fine.
So another question here, and I don't know if you're going to be able to answer this one. This more goes into a business cycle, and I think this is up for individual remanufacturers to assess their business model. But will electronics be considered as good as new and possible to sell as a new item, a new product, or will consumers require a lower price for these types of products? So I think the general question here underlying it is essentially, can cleaning these sensitive electronics bring them back to, OEM specification by themselves, or are there other specific, whether it's thermal cycling, other things that could be damaged on the chip, et cetera, that would prevent, basically just the cleaning process from being the end-all process?
Yeah, I don't. My personal opinion is I don't believe the cleaning process alone is going to render these things as new, because, like you said, there's a lot of other considerations that have to be. I know we do a lot of reman in the military, and the military looks at a lot of things other than just cleaning when they consider reman a part. So, in fact, those parts get stamped, and they only recycle them one time generally. But I'd say the answer is probably no. Cleaning alone is not going to make a part as new.
And what about active versus passive components, like in terms of some of these cleaning options?
Active versus passive. Guess I need a little more clarification. Are you talking about something that?
If the individual on the line would like to type in some more details about what active versus passive components they're speaking about, that'd be helpful in the context if you're still on the call here. As we wait for that individual to perhaps type in more information to provide some more detail, Mike, I think this goes back to, again, the testing procedures and just a business model. Is it possible to evaluate how much life is left in the electronics from a cleaning process through testing procedures, looking at the part? I think that's not really, right?
Not really, no. Not from a cleaning perspective. I know there's a lot of other component testing they do on an electrical component to they hook these things up to diagnostics to make sure they're functioning properly. So I'd say cleaning, it really doesn't have anything to do with that. That's a whole separate criteria.
So there's a little bit of follow-up from the active components, and I believe maybe this individual is referring to things like the chips and processors themselves, perhaps things like VRMs, et cetera, maybe not so much the circuit board. That in terms of active components, I think that they might be referring to.
Oh, you mean like a circuit board, right? Is there?
Right, something that's more, the active, processor involved in the piece of electronics.
And the question is there going to be any significant difference?
Basically, will they need to be replaced? And I think this is a business
I'd
model,
say there's probably
decision.
More than likely when you consider. So let's just take a circuit board that has these active components versus like passive components. The active components in that case are probably more sensitive to any type of damage or contamination, so than the passive parts. So maybe the cleaning of those is going to be more critical. But my guess is there's a higher failure rate of those. just because they are the active component. So there's probably a point where they're not gonna have the same life as the passive component, because those typically the things that are heating up and have to cool, and so but there'd definitely be a difference.
Right. Well, I don't see any more questions at this time. I'll just pause very briefly to allow anyone else to type in their questions as I finish up speaking here today. But I did want to, one more coming in. You did
Sure.
answer that gentleman's question, Mike. He was just thanking you for
Okay.
taking care of that.
Oh, no problem.
So thank you very much, Mike Valenti from Hubbard-Hall, for presenting here today. If you have any follow-up with Mike, we'd be happy to get you in touch with him. And for those of you looking to participate in some of our upcoming webinars, you'll see more details from us soon. So with that, I'm going to wrap today's call. Thank you very much for joining us here today. We had a number of folks on the call.
Yeah, thank you.
Great to see. So thank you, and everyone have a good week.
Thank you.